So if we use a final step in varying the values of PPE from 0.03 to 0.04 to find the value of PPE where the expected outcome of AC option equal to that of the no AC option. So let's look at the table. The value of PPE vary from 0.03 to 0.04, and the step here is much smaller, equals 0.001. So you can see that at the value of 0.032, the outcome, the expected value of the AC option, that equals 0.9919, and the no AC equals 0.9920. The difference very small, so we consider the two schemes the same in terms of the expected survival probability. So in this case, the threshold value equals 0.032, where the two options have the same expected values of the outcome. Right. Next, we talk about another method. Another method for analyzing decision sensitivity is the algebraic analysis. So pretty similar to the numerical analysis. We construct our decision tree as shown on the right hand side, and we also need to define a variable. In this case, we call the disease probability as the PPE. That's the variable we're going to use in our equation. After that, we're going to compute the expected outcome values based on the denoted variables. So look at the tree right here. We denote that the probability of the PE equal PPE, and the no PE is a complement event, so that equal 1 minus PPE. So we want to calculate the expected value of the AC option right here. That's going to equal the expected value of the outcome in this branch multiplied with this one probability of the PE right here plus with the probability of the no PE multiplied with the expected value of this branch over here. So the formula we have expected value of AC equals 0.90 multiplied with PPE plus with 0.9092 multiplied with 1 minus PPE. Similarly, we can calculate the expected value for the no AC option, the same. That's going to be PPE right here multiplied with the expected value of this branch plus with the probability of no PE multiplied with the expected value here. So obviously this one equal 1. So the expected value of no AC equal 0.75 multiplied with PPE plus with 1 minus PPE. So we are finding the value where the expected value of AC equal to the expected value of no AC. So we're going to set the value of this term equals this term. So we have this formula right here, and we solve for the value of PPE that equals 0.032. It's pretty the same with the value we obtained before using the numerical analysis. Right. So next we talk about the a new concept, net benefit and net harm. So many times we use the term net benefit and net harm to express our treatment threshold. So the net benefit, sometimes we call clinical benefit of a treatment, is the difference in the outcome in patient with the disease who receive treatment and similar patients who do not receive the treatment. So the formula to calculate it equal a net benefit equal utility of the treatment given the disease minus the utility of the no treatment given the disease. So here the utility defines the value of the outcome to the patient in the case of desirable outcome. So in our example, technically that's the survival probability. And two of the options we have right here, that the anticoagulation versus withholding anticoagulation. So the difference here gonna be the treatment of the AC given the disease. So that's going to be 0.99. The other option right here is no treatment given the disease. So this one, the survival rate goes 0.75. So the difference of the two utility right here equals 0.24. That we call net benefit. If we use the undesirable, we call this utility function. So for example, right here, this utility expression equals 0.01 minus 0.25. That's equal minus 0.24. This is called a reduction in mortality of the 0.24. All right, another concept we call net harm. So the net harm of a treatment is to define the difference in the outcome between the patient without a disease who don't receive the treatment and a similar patient who do receive that treatment. So the formula to calculate the net harm equals utility of no treatment given no disease minus the utility of the treatment given no disease. So in our example, the net harm of the treatment is the difference of the outcome between withholding anticoagulation versus anticoagulation. On this without the PE. So technically, we look at the decision tree right here. The difference between a no PE and no treatment right here. So the outcome going to be 1. For the other option, that the AC and no PE, the outcome equals 0.992. So the difference or the net harm right here equal 0.008. So in this case, we are saying that no treatment increased survival by 0.008 compared to the treatment, or treatment decreased the survival by 0.008. The formula to calculate the odds and so the probability of the treatment threshold as shown over here. So we have the odds at the treatment threshold equal P over 1 minus P, or equal net harm divided by net benefit, where net harm and net benefit we have been calculated as we discussed before. The probability at treatment threshold equal P of the net harm divided by net harm plus with the net benefit. So we can use this one to calculate the odds at the treatment threshold, the probability at the treatment threshold. All right, next we talk about one-way, two-way, and n-way sensitivity analysis. So up to this point, we have done one-way sensitivity analysis. That the value of one probability will vary or change, while the other probability and the outcome value remain constant. However, in many scenarios, we want to the effect of the simultaneous change in the variable as well. So in this case, if you change the two variables at the same time, we call two-way sensitivity analysis. So here's an example on the right-hand side right here. We would want to see the threshold PE. If the risk of the fatal recurrent PE changing together, what the decision gonna change or not. So in this case right here, we're using the graphical plot to show in that the value of the probability of PE versus the probability of the fatal recurrent PE right here. So the gray area right here, that's the AC, and the dark area right here, that's a no AC. So at any point, if we have the value of the PE equals 0.25, for example, and the probability of a PE equal 18, for example, so that's gonna be 1 point right here. So this point in the region of the AC, that means the AC scheme is the better choice, or has a better survival probability. So by combining and changing the values of two variables at the same time, we have a two-way sensitivity analysis. In many scenarios, we changing multiple variables at the same time. For example, we change the setting. We have a different patient where the characteristics very different, so we call that n-way sensitivity analysis. In this scenario, we have multiple or n variable change at the same time. So by quantifying and also looking at the changing of the outcome based on the changing of multiple variables, we call that the n-way sensitivity analysis. So do and don't of the tree building. So in the tree building, diagnostic test to obtain additional information is worthwhile only if at least one of the decisions would change by the test result, and if the risk to the patient associated with the test is less than the expected benefit that could gain from the subsequent change in the decision. So in our example, we can model the decision to obtain the diagnostic information by adding this option as well. So as before, we eliminate the third option, but actually we can put that third option into the consideration as well. So in this case, after performing the CT pulmonary angiogram, we are again faced with the choice of whether or not to give the anticoagulation, AC versus no AC. So that the decision tree contains the embedded decision node in this scenario as well. So the example we show right here, the first decision node, we have the AC, that the anticoagulation. In no AC right here is mean withholding the anticoagulation. Now we have the third choice right here, just CTPA. This means CT pulmonary angiogram. So after this one, we also have the two possibilities that the chance node. In this case, we have additional information, but the outcome here is still not certain. So we have some probability that's gonna be PE, and some probability that's no PE. And after this outcome, we also need to take the decision, should the anticoagulation be selected or not. The same here. So in this case, we can see that the decision tree obviously more complex than previous example, but the structure gonna be pretty the same. After the decision node, we also have the leading action, and then we also have some chance node followed by that specific action, and we're building up the tree based on the alternative action we have. So in order to simplify it, we call a decision tree in strategic form. In this way, we remove the branches that would never apply anyway from the decision tree compared with the extensive form we have over here. At this point right here, we have the strategic form of the decision tree.